Previously in another video, I showed a proof for the ideal gas law, which is written as PV equals nRT. And the proof that I used was this one. It uses a bunch of laboratory-derived proportionality arguments to reach our conclusion. However, I found that I really didn't like how kind of arbitrary this was. Used a lot of rules to gain this, and just making a simple proportionality argument and then somehow coming up with the constants didn't seem very rigorous. But I found another proof online. If you want to look up the video that I watched, it was by Cyrus Larijani. And the name of the video is The Ideal Gas Law, a Theoretical Derivation. So that will be who the credit belongs to for teaching me this proof, and which I am then showing here. So what you do is you have this box of size L, any box, and let's just say we have a single particle here and it crosses a length L and hits the wall and has a, I guess you could say, perfectly elastic collision, and it bounces back with the same momentum. So just to define some terms, we have d for distance, m for mass, vx can be our x velocity. So just write that, x velocity. And momentum we'll call little p, which is mass times velocity. So this can would actually be called x momentum. And we know force is equal to mass times acceleration, and since acceleration is delta vx delta t, the change in velocity over time, then we will have that we can plug this in. We have m delta v delta t equals delta p delta t. So the force is actually the change in momentum over time. And let me just, to make things a little bit more, I think, yeah, we can call it F, force in the x direction, velocity in the x. You could also call it px, x momentum. And so to figure out what the x momentum is, we just say, we give it two momentums. One is when it's going this way, it has a negative velocity x, so negative mvx. And on the way back, it's positive mvx. And we know that delta of f is equal to f2 minus f1. So that's why we have the minus here. Then we got negative 2 mvx. We also know that velocity is velocity equals dx dt, so it's a change in d distance, and the distance it travels is 1l, 2l, so it's 2l over t. And you can solve this for 1 over t delta t, which is equal to vx over 2l, and plugging that in here into force, we have force x, px. Then we will get negative 2 mvx squared over 2l. The 2's cancel out, and we'll get this expression for force. So it's mvx squared over l, negative. We could have done this with the partial here going this way and back, and then this would be positive, I think. So, but it doesn't matter for the purpose of this. So now we include n particles or molecules instead. And so the total force would be the sum of this. And let's just get rid of the negative, because we can, let me see. So if it's this way mx minus negative mx. Yeah, so it would be positive. It doesn't really matter the sign, because either way it will cancel out. So in this case, we'll just say it's positive. So the total force will be total force in the x direction. We'll just call it F total, so we don't have to write like Fx total. It'll be kind of annoying. But we'll just call it force total, and it's equal to m over L, so take m over L, and then it's the sum of many Vxj's. So this sum will go from j to n, so that's equal, so this sum here will be Vx1 squared plus Vx2 squared plus dot 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 up to Vx n, or sorry, capital N squared. We also can define the average, which we put a bar over Vx squared, is 1 over n sum up to n of Vxj squared. So we can actually plug this into this equation, and you can see that these terms are the same. We'll just need to put n on top here, so nm over L. So that's the total force. Now the total pressure is the total force over area, and area is L squared. If we take this and plug this in, we'll get nm over L cubed Vx squared bar, or average. And L squared is the volume of this cube. So we can move the volume to the other side. We have PV equals nm Vx squared. So this looks a lot like PV equals nRT. So we're almost there. Now, if we have multiple velocity directions, then we can define the magnitude of velocity, which instead of being a Vx, it will be, well, this is actually going to be the average velocity. So the average velocity magnitude squared, because you know a magnitude is if it's magnitude of f, where f is like a vector, then it's fx, the square root of fx squared plus fy squared plus fz squared, and if you square both sides you get rid of the square root, and so we have this vx squared plus vy squared bar plus vz squared bar. And so these are actually, the square is under the bar, so the average of squares. A big assumption that we make here is that the average velocities in either direction are about average. So you have many random particles going in many different directions. So we can pretty safely assume that overall the particles are moving, the molecules are moving at the same sort of speed. But this is a big assumption for the ideal gas law. And if it's not true, there might be more calculations that are needed. But I think it's probably a pretty safe assumption to make. But I'm wondering if maybe there's a proof that extends this where that's not the case. And so because we're assuming they're all equal, we can just say it's Vy or Vz, Vx, 3 times Vx squared bar. Again, with each of these, it's a bar. This one, I think, the magnitude here. So I think, yeah, a better way to do this is all right, yeah, this is just V, but each of these are going to be squared. So Vx, so this is Vx. I see. Okay, so actually I was incorrect when I was saying that. So these squares go above for all of these. Because yeah, we define the magnitude as having, the magnitude obviously has these squares in it. So this term is just the magnitude of the averages and then the squares outside. So now that we've done that, we can plug it into PV, which was this. So it's NM divided by 3, the magnitude of the averages squared. And now we can play some trickery. We multiply by 2 divided by 2, which is 1. And we can see that 1/2 mv squared is kinetic energy. But another definition for kinetic energy other than 1/2 mv squared is F over 2 kT, where F is equal to 3, gives us 3/2 kT. Now, what is F? F is the number of degrees of freedom of the gas. So how many directions can it go, which in this case is 3 directions, X, Y, and Z. And K is the Boltzmann constant, T is temperature. So now plugging that in, we'll get 2/3 and 3/2 kT. These cancel out, we get nkt. Now we can define the gas constant, or it's the general gas constant, which is equal to Avogadro's number times the K-Boltzmann's constant, where Avogadro's number is how many molecules you have per mole. It's simply a unit of measurement that's created. So it's not like necessarily like some actual new quantity, but Na times K, we just define it as our constant. We just make our constant like this. They're both constant numbers, so we can make whatever constant we want. Now plugging that in, we'll get N over Na, so number of molecules times the number of molecules per mole will give us this quantity called N, which is the number of moles. And just to be clear, this is the whole thing is N. So we'll have nRT, PV equals nRT. So that's what we're trying to solve for. Now that we have it, 2 different ways, I like this way better. We can then say our general gas constant for a specific gas constant, is the gas constant we had before divided by mg, which is the molar mass of your specific gas. So like we could do MO2 or MCO2. That could be our gases. So we've defined this, we plug it in, we'll get N stays there, we'll have this mg times rg, and then we can define mg is big M, which is our mass, which I think we can call, actually let's call it little m. So we have our mass, which is number of moles, so moles times the molar mass of the gas, which is how much mass per mole. So we say we multiply N times mg, so N times mg is equal to, in terms of units, it's the moles times the mass per mole, which is equal to the mass. So that's why it's M. And so now we have PV equals mRGT. So that's what we were looking for. And finally, we can define density is equal to mass per volume. Or that's the same thing as saying that alpha is equal to volume per mass. Or we just define another one called alpha, which is the inverse of that. I'll just do that because I like to write it this way. Then we have PV over M. So P alpha is equal to what we have, PV over M. So take this m, divide it, PV over m is equals to RGT. So now we have P alpha equals RGT. And yeah, that's our equate. That will be our ideal gas law. So just like highlighting green, so it's like shows the final version. Okay, and just to give an example, so we can say P alpha equals RDT for dry air. Or we can say P alpha equals RVT for water vapor, etc. And then also, just to write down here, rho is density, and alpha is, I guess you can call it like inverse density. There's a word for it. Oh, I think it's specific volume. And also, if anyone's wondering what does specific mean, I think it just means you divide it by the mass. So volume divided by mass goes from volume to being called specific volume. Okay, great. Thank you for watching, and stay tuned for more videos in the future, and have a good day.